Hello everyone, welcome to this lecture video for Math 116, Combinatorics. And in this video we're going to talk about graph colorings as an application of the inclusion-exclusion principle, which was the previous video. So we haven't actually really talked about graphs yet, but let me define it. A graph is a set of vertices. That's just what they're called. And usually it's denoted V for the set, and then some set of size 2 subsets of the vertex set called the edges. So here's an example. Here are 4 vertices, 1, 2, 3, and 4. And then the edge set is a bunch of subsets of size 2, and I'm drawing them using lines. So 1, 2, 1, 3, 2, 3, and 3, 4 are all in the set. And if two vertices are create a size 2 set that is in E, they are called adjacent. So in the picture, there's a line exactly when vertices are adjacent. A proper coloring, or simply a coloring, of a graph for a given set of colors C is a function from the vertices to the colors, such that whenever you have two vertices that are adjacent, then they have different colors. So here is a coloring of the graph from the previous slide, and we can using the set of these 4 colors, and we can see that in this, like blue and red are different colors, green and red are different colors, green and blue are different colors, and red and blue are different colors. So it's a proper coloring. This coloring is not okay because red and red are adjacent. So that's all there is to it. And so one question is, well, one really basic question, does a graph have a coloring at all? And then the next question is, how many does it have? And so we're going to give a way to calculate that in a pretty straightforward way using the inclusion-exclusion principle. Yeah, so our formal question, how many graph colorings for a given color set C does a given graph have? So here's an example, a 3-vertex graph where with only 2 edges, and let's consider the set of 2 colors, blue and red. So once we color the first vertex, then that forces the second vertex to be the second color, which then forces the third vertex to be the first color again. So there are only 2 different ways to color this graph. Okay, so to do this calculation, the idea is we're going to try to write F as a coloring in terms of sets, in particular somehow involving a union of sets, because then we can apply the inclusion-exclusion principle. So for every edge, let's let S sub that edge be the set of all functions from V to C. They're not colorings, they're just assignments of colors to vertices, but with the property that the 2 vertices that are adjacent along that edge have the same color. So for example, if we have this graph and let's say that this edge is labeled E, also I want this to be in a different color. Okay, so if that's labeled E, then one possible coloring in SE, not coloring, but an assignment of colors could be both blue, maybe this one red, for example. There's also all of them the same color, that's fine. But if these 2 have different colors, then it's not in it. Okay, so let's see. Let's look at not F as a coloring, because that's going to be a little more convenient to manipulate. So that is equivalent to, so what is F as a coloring? Remember, that's for all edges, that should be not equals. For all edges, the vertices that are incident to that edge have different colors, right? And then not for all is the same as exists not. So we get a double negation that cancels out. And so f is not a coloring is equivalent to saying that there exists an edge where the vertices get the same color. That makes sense. So now we can write this as a union, because if it's the case that there is an edge where f has the same color as the adjacent as the vertex across the edge, then there is some edge such that f is in SE, because SE is the thing, it's the collection of all functions where the same color lies on either end of that edge. So f is a coloring is equivalent to saying that f is not an element of the union of these sets. So let's start invoking that inclusion-exclusion principle. I've written the definition of S in the upper corner so that we can reference it. Okay, so the number of colorings then is the collection of all functions. And remember, this is the set of functions v to c. And so it's all functions that aren't in the union of all these SE sets. And because this union is a subset of the set of all coloring of all functions, then we can turn this into a difference of cardinalities. And then because the second thing is a cardinality of a union, we can use the inclusion-exclusion principle, which says that we can sum over all numbers of subsets of indices, namely or 1 through, we'll deal with, how many how many of these sets are we going to intersect in that particular term? And that's 1 through the number of edges. And then there's this minus 1 to the k plus 1 factor. And then we're summing over all size k subsets of edges of the intersection of these SE sets for that particular size k subset. Okay, so that's the inclusion-exclusion principle. And if we interpret this set here, this intersection is saying that it's all the functions g from v to c, such that for every edge in that set H, the vertices are given the same color. And then also, there's this thing that we can observe, which is that in the second thing I wrote, I started at k equals 0 instead of k equals 1. When k equals 0, then we've got plus sum over size 0 sets of this cardinality. And what happens when k is 0? What's the size 0 set? That's the empty set. And what happens if this is the empty set? This for all is vacuously true and we don't need it. So when k is 0, this is simply counting the number of functions from v to c, which is this first term here. So we can subsume it into the sum. Okay, now that we've done that, we don't really need to do this double summation thing. We can just sum up overall subsets and then do minus 1 to the cardinality of that subset. Just simplifies the equation a little. Okay, so the number of colorings then is this formula. The sum over all subsets of edges of minus 1 to the number of edges of the cardinality of functions assigning colors to vertices such that every pair of adjacent vertices with respect to the set of edges have the same color. So let's look at an example. And I've got this formula in the upper corner for our reference, which it looks like I accidentally turned purple. So we've got this 2-edge graph that we looked at before for coloring it with 2 colors. And first, let's look at all possible subsets of the edge set. So it's only 2 edges, which means that there are 4 possibilities: the empty set, the left edge, the right edge, or both edges. And I've written the edge sets on the graph so that we can or I like taking a look at the graphical version. So then let's record -1 to the number of edges. So that would be -1 to the 0, which is 1, then -1, -1, 1. And then here's the question. For each of these situations, we want to know what the cardinality of this set and this sum is right up here. So remember, these are functions that color the vertices using C, where for every edge I've drawn here, those vertices have to have the same color. So what that means is that one of them is sort of, we can choose one of the vertices, say, to be the thing that actually controls what the color is for everything that's like transitively connected to it. So for here, there are 3 distinct vertices that are not controlled by any of the others. Then here there are only 2 vertices that we need to set. If we set the first vertex, then the second vertex follows along, and then the third vertex is independent. And these are the only 2 vertices that we need to color, and then everything else comes along. And also, this is arbitrary. I'm just choosing one of the vertices. That's for sake of explanation. That's fine too. And then if we have both edges, and the first vertex has to be the same color as the second vertex, has to be the same color as the third vertex, that just means they all have to be the same color. So another word for these regions that I'm trying to count are components, which are all the vertices that are transitively connected to each other, like each independent region of those. So 3 components, 2 components, 2 components, 1 component. And then, so then to count the number of colorings, it's in each, these cardinalities, we can take the number of colors to the 3rd power for the first situation, number of colors to the 2nd when there are 2 components, and just the number of colors to the 1th power when there's only 1 component. And then by using the pluses and minuses, then we get it as a polynomial in terms of the cardinality of C. And I've factored it just for, I guess, fun. One thing to notice about this formula is it has a combinatorial interpretation, which is we can think about the fact that once we've chosen the color of the central vertex, then that means that we can choose the colors of the other 2 vertices independently, but so long as they're from the remaining colors. So this is the central vertex, and then this power of 2, each of these are for, I guess, the wing vertices. Anyway, if we calculate colorings, one thing we can see is that when we have 0 or 1 colors, there's no ways to color this graph. It's kind of obvious with 0 colors that's impossible, but with 1 color, that would mean that they're all the same color, but that's not allowed for proper coloring. We already calculated that for 2 colors, then that would give you 2 different colorings, and I've calculated the rest. So just one more example that ties into some stuff we've seen before, which is color, like how many injective functions are there? So, okay, so one special kind of graph is called a complete graph, and that is when all possible edges are in the graph. So when E is the entire set of pairs. So this is a complete graph with 5 vertices, and that's a complete graph with 3 vertices. So the thing is, when you have a coloring of this graph, what's happening is that every pair of vertices has to have a different color, and that's exactly the injectivity definition. So that is counted by the falling factorial function, which, remember, in this case it's slight mistake. I meant to start off with C right here. Okay, so it's the cardinality of C minus 0 times the cardinality of C minus 1, all the way down to the cardinality of C minus V plus 1. And that like, what's the interpretation? You color the first vertex, then you can color the second vertex with any of the remaining colors, then the third with any of the remaining colors, and so on. But using our formula that we have derived using inclusion-exclusion, we have that the this following factorial is the sum over all size 2 subsets of the vertex set of minus 1 to the number of edges there times this cardinality. And so if we try it with this graph with only 3 vertices, and I did 3 because, well, you know, there are a lot of edges otherwise, and this one already has 8 things to consider. Okay, so this is the empty set, just the bottom edge, that's just the top right edge, and so on. All 8 possibilities. And here's the calculation of minus 1 to the number of edges. So 1 minus 1 minus 1 minus 1, and so on. And like before, to count this cardinality of these coloring, of these functions from vertices to colors, where vertices that are adjacent with respect to h have the same color, remember it turns out that it's the number of components. So 3 here, 2 here, 2 here, 2 here, and then all the rest, there's only one component, because if we color the first vertex here, then all the other vertices have the same color. And similarly, if we color any of those vertices, they all have the same color. Okay, so to calculate the number of colorings, which is, as we've said, should be this, we can then add up all the terms in this, and we get a polynomial. And so if we write like simplified, I guess we get this polynomial in the cardinality of C. And notice if we factor it, we get the following factorial as expected. Yeah, so it's a fascinating thing. It turns out that the number of colorings of a graph is a polynomial in the number of colors. And this is something we'll talk about more when we actually talk about graphs more later in the quarter. So anyway, that was an example of inclusion-exclusion and how it has to do with graphs. See you next time.